Changes in entropy. Exothermic reactions tend to be spontaneous reaction. This means that as long as sufficient number of particles have energy above the activation, the reaction will proceed by itself until equilibrium is reached. Looking at the reaction for this reaction more closely, you can see that 4 moles of the reactant form 7 moles of the product. So first factor is the increase in the number of species, 4 moles converting into 7 moles. Plus, in addition, carbon dioxide gas is formed, and a gas is more disordered than either a solid or a solution. Both these factors result in an increase in the entropy. So if you are given a type of the example, you will determine whether the entropy will increase or decrease simply by looking at the equation. So for this type of the equation, you will check how many species are on the reactant side and how many species are on the product sides, plus what is the state, change in the state. Here we see that this molecule is in solid and this one is in aqueous, whereas in the product side we have one species in the gaseous state as well. So gaseous state will also increase the entropy value. So both these factors are actually influencing the higher entropy value. If there is a sufficient increase in entropy, the system will favor the change, and the change is said to be spontaneous. The increase in entropy in the reaction between citric acid and sodium carbonate explains why the reaction is spontaneous. So spontaneity is related with the entropy. Higher the entropy value, the higher the spontaneity, or you can say more disordered reaction has a spontaneous reaction. Spontaneous reaction is linked with the higher value of the entropy.
Wait, hold on. What is the connection between spontaneous reaction?
Spontaneous reaction has a positive value, has the greater value of the entropy. Increase in entropy means spontaneous reaction. If there is an increase in this entropy value, the reaction will be of spontaneous type. Then we have changes in state. When ice melts to form water, the particles move further apart, have more energy and more disorder. The entropy of the system has increased. When liquid particles change to gas, there is an even greater increase in disorder as the gas particles move with much higher energies and a greater random arrangement. This is the chart which you can see here. For changes of state for all substances, entropy of gas phase is much greater than entropy of the liquid phase, which is greater than entropy of solid. So this is the order wise entropy. Entropy of gas is very much greater than liquid, and liquid is somewhat greater than the solid. You can see this in this graph. This type of graph is also in your Laurentian book. Here we can see these two graphs. I guess it is on there. This graph is in Laurentian book, and similar graph is in this book. You can see here when solid is melted, it shows this degree of increase in entropy, because along the y-axis we have the entropy. This is a smaller increase in the entropy value when solid melts into the liquid, and then when liquid boils, converts into gaseous state, then this increase of entropy is seen. So you can find the difference. This is smaller increase in entropy, and this is much greater increase in the entropy value. So solid to liquid shows smaller increase in entropy, and solid liquid to gas shows greater increase in entropy. Although changes of state, solid, liquid and liquid to gas are endothermic and require energy, the changes are spontaneous because they lead to an increase in entropy. So you have to memorize all these points when you are finding the change in the entropy. You have change in the state, you have number of species, how many species are present, and then we have the complexity of the molecule, which one is smaller, which one is the greater, plus there is also a link with the temperature as well, like if the reaction is endothermic or exothermic. So we'll continue this in our next class, and we'll consider all the points to determine the entropy. All right.
Yeah.
So meanwhile, try to attempt the questions. I will make a new worksheet for the entropy and our next topic, Gibbs free energy. I will include questions for these two topics now. All right. So we'll meet in our next class now.
Thank you, sir. Allah Hafiz.
Allah Hafiz. Alright, so last time we had completed up to this graph. Is there any question from previous lecture?
To be honest, I'm kind of having some trouble, with this entropy thing. Just this, spontaneous reaction part.
The spontaneous reaction part?
Yeah.
Spontaneous. Where is it? Spontaneous. Spontaneous means the reactions which occur by itself. And in terms of the chemical reactions, the spontaneous reactions are those which are mostly exothermic. Exothermic, just like we discussed the electron affinity, then hydration enthalpy, and then enthalpy of solution in those type of the reactions, and plus the lattice enthalpy as well. In these type of the reactions, the energy is released into the surroundings because the product which is obtained is more stable as compared to the reactants. So such type of the reactions which give you a stable compound, a stable product, will be termed as the spontaneous reaction. Do you get this?
Yeah, let me just write that really quickly.
Okay. Is there any way if you can switch on your camera and put it on your put the direction on your notebook so I can see you working?
If I do that, then I won't be able to see the screen.
Sorry?
If I do that, I won't be able to see the screen.
Okay.
Anyways, I'm done now. That's all I have to write.
All right. Do you have an extra camera with you or not? A wireless? No. Okay.
Anyways, I don't take long to write anything.
I do understand it, but it gives me an overview of you working. Anyways, so have you written it?
Yeah, I've written.
Okay. Give me a second. Okay. Now we start from here. The changes in entropy when solid dissolves. From the previous graph, you can see that the entropy is greater for the liquid state as compared to the solid, and then the entropy is even more greater for the gaseous state with respect to the liquid. So this will be discussed here in these topics. Changes in entropy when solids dissolve. When soluble solids dissolve in water, they go from a highly ordered state to a less ordered state. The entropy of the system increases. The particles are released from their positions within the solid, usually lattice structure, and can move more freely. The entropy increases not only because there is less order within solution, but also because more free moving particles are produced as a result of the change from the solid to solution. So this is the process by which we can see that the entropy increases. Entropy increases when solid is converted into the solution form, because in the solution form the particles have more degree, more ability to be disordered, because within the solid the particles are in the ordered form. In this type of equation, we have 1 mole of the sodium chloride in the solid state converted into the 2 moles of the ions in their solution form. So because of the two reasons, the entropy increases. The first one is the change in the state from solid to the aqueous form, plus the number of moles are increased from reactants to products. There is 1 mole of the reactant and there are 2 moles of the product. Same goes for this equation. We have solid ammonium nitrate, which is converted into the aqueous ammonium ions and then aqueous nitrate ions. Is it clear?
Yes.
Changes in entropy when products are gases. Now definitely the gases will be having the greatest amount of the entropy. In any chemical chain, in gas molecules are produced from a solid or liquid, there is an increase in entropy. This makes such reactions spontaneous. Spontaneous, here again it is described. It is also the reason why certain endothermic reactions are surprisingly spontaneous. Spontaneous means that the reaction is occurring automatically because the products are having the larger value of the entropy. When there is an increase in the entropy value, the reaction type will be spontaneous. Here in the decomposition of calcium carbonate, we get 2 types of the products. The first one is the calcium oxide, which is the solid, and the other one is the carbon dioxide, which is the gas. So you can see there are 1 mole of the reactant and 2 moles of the product. So because of this change in number of moles, we have an increased entropy, plus the state of one type of the product is gaseous. So this gaseous has very high entropy value. So again there is an increase in the entropy. The reaction results in the formation of carbon dioxide gas. This increases the entropy of the system. So the reaction is spontaneous. And now in this type of the reaction, we have water of crystallization here. Are you familiar with this type of the product?
Yeah.
Water of crystallization, by heating such substance here.
Yeah, when you heat it, it loses the water, and when you add it again, like, this is with salts, right? Like pink and B.
Yeah. Loses water upon heating and bonds with water molecule upon what? Adding water plus filtering and cooling. So
Yeah.
we have this. Again we have 1 reactant and 2 products. Then 1 product is in the gaseous state. So this is an increase. This is type of the entropy increase. Predicting entropy changes. This is the summary. We can combine all the ideas we have covered about entropy. Number one, a negative entropy change will lead to a decrease in entropy, and there is a greater order. So negative entropy means decrease in entropy, and decrease in entropy means greater order. Positive entropy means increase in entropy, and there is a greater disorder. And this point, for a change in which there is little change in disorder, the entropy change will be close to zero. So if there is a small value,
What do they mean by greater order?
Greater order is the opposite of the disorder. Like solid substances have greater order, but liquids have greater disorder. Or you can also say that if we reverse this reaction, by adding water into the copper sulfate, we get this crystalline compound, water crystallization compound. This will give you a decrease in the disorder, because we are making one compound out of two reactants. What I mean to say, if you move in the opposite direction, so this will give you a decrease in entropy. Change in entropy will be decreased. Is that so?
Yeah.
So this means it is the negative entropy, and it means more disorder or greater more order or greater order. Greater order. Okay.
Yeah.
And the last point, for a change in which there is little change in disorder, the entropy change will be close to zero. It means that if we have only a small change in the value of the entropies in the reaction, the entropy change will be close to zero. This type of the reaction will be discussed in this example, and I guess the example is in the Laurelian book, in the second book. Here we have work example. What would you deduce from this type of the reaction? What should be the entropy change?
It will be negative.
Why?
Because on one side, on this reactant side there's 4 moles, and on the product side there's 2 moles. So this is going to cause a decrease.
Yes, it is a decrease. So there shall be how would you define in terms of the order or disorder? How would you state in terms of order or disorder?
There will be greater order.
There will be a greater order. So the entropy change will be negative. Calculating entropy changes. This is the mathematical equation. To calculate entropy change, we can calculate the entropy change for any reaction given the entropies of the reactants and the products. The entropy change is the difference between the sum of the entropies of the products and sum of the entropies of the reactants. So this is the equation used to find the entropy change of the reaction, products minus reactants. Here is the work example. Calculate the change in entropy for the reaction between hydrogen and chlorine. We have this equation. What do you say? How would we write this question in terms of this equation? How will we solve this question?
Would it be for the first one, 2HCl, minus H plus CO2.
What should be the values?
2 minus 2.
2 minus 2.
Oh no, wait, I realize now that the values are given. 1 minute, let me think. Just give me a minute.
Okay. Moving forward. This was all about the entropy from this book. Let's see something different in the second book. Entropy is the measure of dispersal of energy, and plus it was the randomness or disorder of the system. Then we have entropy can also be thought of as dispersal of energy either from the system to the surroundings or from the surroundings to the system. The system becomes energetically more stable when it becomes more disordered. So stability is linked with the disorderness. Greater the disorderness, greater will be the stability and greater will be the entropy. Values you are need to find the values of entropy is in joule. The unit should be joule per Kelvin per mole, not the kilojoule. Remember that elements have positive standard molar entropy values. Do not mix entropies up with the enthalpies. The elements in the standard states have enthalpy values of 0. So elements can give you a positive value. It will not it means that the entropy of the elements still have some value, but enthalpies don't have the values. They are actually 0. So this is difference here. All perfect crystals have same entropy at a temperature or absolute 0. And then we have discussed the gases generally have much higher entropy value than liquids, and liquids have higher entropy values than solids. There are exceptions to this. For example, calcium carbonate, which is a solid, has a higher entropy value than mercury, which is in the liquid. So exception exists here. What do you think? Why is it happening here that solid has greater value but liquid has a smaller value?
Because of higher, stronger intermolecular forces.
Stronger forces, intermolecular forces. Calcium carbonate, what type of forces exist between calcium carbonate?
Would it be like dipoles or equivalent?
No. Calcium carbonate is an ionic compound. Calcium carbonate. So there doesn't exist any type of the covalent or intermolecular forces. But mercury, what about mercury? Mercury is a metallic compound. So there are just metallic bonds within this molecule. The reason why there is an exception here is that calcium carbonate is a complex structure, whereas mercury is a comparatively smaller, because it is based upon only the mercury elements, mercury atoms. But calcium carbonate contains so many elements, so many atoms here, which is discussed here. Simpler substances with fewer atoms have lower entropy values than more complex substances with a greater number of atoms. So this compound has greater number of atoms with respect to mercury. So we can say it may be because of this reason why mercury has a smaller entropy value. Then this point, for simpler types of substances, harder substances have a lower entropy value. For example, diamond has a lower entropy value than graphite, and calcium has a lower entropy value than lead. So this is an additional point. Hardness has smaller entropy value, and soft substances have greater. Why is that so?
To be honest, I don't know.
When do we have a greater entropy value?
When
there is a greater
we have the greatest disorder.
So harder substances, isn't that hard to break the atoms in the harder substance?
Yeah.
Right. So harder substances will require greater amount of energy to break apart the atoms. So only then we will have a greater disorder. That's why harder substances have a lower entropy value, because there is a lower disorderness in it. But other soft substances, they will have greater entropy value. And then entropy, we have discussed this already about the change in the state. Where is it? We have already discussed this thing. Entropy increases as solid melts and then changes to a vapor. According to this graph, there is a clear-cut change in the melting and boiling point. Entropy values changes. There is smaller value at the melting point with respect to the boiling point. Now the reverse phenomena. Note that when a gas condenses to a liquid or liquid changes to a solid, the entropy decreases because the more particles are going from more disordered state to a more ordered state. And same goes for the no, that's not. Entropy changes in reactions. According to this, we have discussed already that there is when we decompose calcium carbonate, we get this 2 moles of the products, and the carbon dioxide is in the gaseous state, so that entropy increases. What about this equation? We have 2 moles of the reactants and 5 moles of the products, so the entropy should decrease.
Yeah, because greater order.
Yeah. And then calculating entropy changes in endothermic and exothermic. It is now linked with the type of the enthalpy. Energy can be transferred from the system to the surroundings, exothermic change, or from surroundings to the system, endothermic. For an exothermic reaction, the energy released to the surroundings increases the number of ways of arranging the energy. This is because energy goes into rotation and translation of molecules in the surroundings. So there is likely to be an increase in entropy and increased probability of chemical change occurring spontaneously. In other words, the reaction becomes more feasible. So according to this, exothermic reactions will be more feasible, they will be more spontaneous, so entropy will increase. Entropy of the surroundings will increase. But for endothermic reaction, there is decreased probability of the chemical changes occurring spontaneously. So entropy is also linked with this exothermic and endothermic. Is it clear?
Yeah.
Total entropy change, you do not have to know the equation. Delta S total is equal to delta system plus delta surrounding. This equation is not required for your examination, but they have used this equation to solve many numericals in this literature. So we will go through this equation as well. Actually, the right equation to find the delta, the entropy change, is in the other book, which you can see here. This delta S, which is equivalent to delta S products minus reactant, this delta S is the system over here, delta S of the system. Delta S of the system is equal to delta S of the products minus reactants, whereas if you want to find the delta S of the total value, so you will also have to include delta S of the surroundings, which is actually added into the system. There is a different equation to find the delta S of the surrounding, which is mentioned in the letter. So do memorize all the equations when you are required to find specific value. If the total entropy change increases, the entropy change is positive, the reaction will then occur spontaneously. We say that the reaction is feasible. So increase in entropy means reaction is spontaneous and reaction is feasible. They have somehow also mentioned the difference between spontaneous and feasible. Spontaneous can be referred to both physical and chemical processes, whereas feasible is referred only to the chemical reactions. So this type of any type of the reaction which has a increase in entropy will give a feasible reaction, and this is the vice versa. Then a question is here: calculate the entropy change of the system for the reaction. For this type of the reaction, we are given the values for all the reactants and the products. So simply in the same way which you did, calculate the entropy of the system. So here it is the delta S of the system which you actually found before, whereas here it is the delta S of the total. So delta S total is equal to this equation, and delta S system is equal to products minus reactants. So you will apply the same calculation and you get this value. The negative value for the entropy change shows that the entropy of the system has decreased, which we know how the calcium reacts spontaneously with oxygen. So the entropy of the surroundings must also play a part, because the entropy change must be positive for the reaction to be feasible. So this type of the reaction is not feasible. Then here it is the formula to find the delta S of the surrounding. Again they have said that for you you don't have to know the equation for your examination, but the equation is useful for general understanding of entropy. So here it is the equation to find the delta S of the surrounding. The equation is minus delta H of the reaction divided by time, minus delta H reaction. It is the enthalpy of the reaction divided by time. So delta H reaction is the standard enthalpy change of the reaction. T is the temperature in Kelvin. At standard temperature, this value is 298 Kelvin. We are studying this topic in the standard condition, and according to standard condition, the temperature is 298 Kelvin. Do not confuse this with the STP. STP means standard temperature and pressure. What is the value for standard temperature and pressure?
I think the standard temperature was 24 degrees Celsius, and this pressure was like the standard pressure was 1 atmospheres.
Okay, this which you have given me is correct, but this is wrong. Standard temperature is equivalent to 0 degrees centigrade.
I know, this pressure and this standard temperature.
Standard temperature is equivalent to 0 degree centigrade, which is equal to 273 Kelvin, and room temperature and pressure is equivalent to 20 to 25 degree centigrade. This 25 degree centigrade is equivalent to 298 Kelvin. So do not confuse yourself with standard, that standard means STP. No, it doesn't mean by this. Standard doesn't mean by STP. Standard here means RTP here, because this value is actually the room temperature and pressure. So you have to memorize these values. Whereas the pressure has same value in STP and at room temperature, which is actually 1 atm, in both the conditions, in the STP condition and in the room RTP condition, it is actually equal to 1 atm. All right.
Yeah.
There is a question. Calculate the entropy change of the surroundings for the reaction. Surroundings. So when you are required to find the value for the surrounding, then you have to put this formula. For this we need delta H and temperature. Delta H is given, temperature is understood, which is 298 Kelvin, plus what you else have to do, you have to convert the enthalpy change into joule by multiplying by 1000. Delta H is given in kilojoule, but delta F has to be determined in joule. So every time you are required to find this type of the reaction and this type of the equation, you have to convert kilojoule into joule, which is very easy. Simply multiply by 1000. They have said this before somewhere above. Or maybe later. Total entropy was equivalent to this, and we can replace this delta S surrounding equation with its own formula, which is delta H ratio minus T, and you can also replace this delta S system with its own formula, which is what?
This delta S total equals delta S system minus negative delta H reaction divided by T.
No, I meant to say you can replace this delta S system by its own formula.
So like delta S total minus delta S surroundings?
Delta S products minus reactants.
Oh. So there's so many different equations.
These are equation for delta S total, just, and you also know the equation for delta S system, and you also know the equation for delta S surrounding. Delta S surrounding equation is this one, and delta S system is equivalent to this equation. Products minus reactants. Entropy in equilibrium reactions. Equilibrium reactions, it's not let's see. In equilibrium reactions, both products and under standard conditions, the overall entropy change is 0. So this is all you have to memorize, that at the position of equilibrium, entropy change is 0. Overall entropy change is 0, because the entropy change for the forward reaction equals the entropy change of the backward reaction. That was all for the equilibrium reactions. Clear?
Yeah. Can you like send the notes for entropy?
Notes. You have this book with you, so you don't need this book, right? Notes like
I have I have the orange book, but from the other book,
Yeah,
it would be helpful.
yeah. I will give you photos from this book for the entropy. Then we have this type of the example, that reaction for this type of the entropy delta S surrounding, which is equivalent to minus delta H of the reaction divided by time. If you apply the temperature factor here, if you want to study that at high temperature the delta S surrounding should be negative, or at a low temperature, simply put the values. If you increase the value of delta T, this will give you a lower value of the overall equation. If you increase T, it will give you a lower value of this delta surrounding. So at higher temperature the delta S is smaller, negative value is smaller, negative value means greater value of the positive. So delta S will be not give you a good value. Like if you apply here reaction at 298 Kelvin, we have smaller value here 298 Kelvin, this will give you minus 242.6 over here. And if you apply 550 Kelvin, then you have minus 131. So at higher value we have smaller value of this. So you can see that at 298 Kelvin the total entropy change is negative, so the reaction does not occur at this temperature. At 550 Kelvin the total entropy change is positive, so the reaction is spontaneous at this temperature. Delta S total also includes the delta S of the system, which is already calculated before over here. So you will go through this example in your book, and you will know how this reaction has been described in terms of the temperature and the enthalpy. The entropy is now completed here. I want to cover quickly the Gibbs free energy as well. Okay.
Okay.
Gibbs free
What
energy.
is Gibbs free energy? What is Gibbs free energy?
We are about to start Gibbs free energy, so you will know what is it. Gibbs free energy is a new topic included into the A2. You can say it is now in a new portion in the A levels. This was not previously included. So
this new stuff is it new things that have been discovered?
Wait a second. No, not this one. Sorry. This topic is already mentioned because I have made the question. The new topic is linked with the electrochemistry. Gibbs free energy when linked with the electrochemistry. That is a new thing included into the syllabus. So when this Gibbs free energy is linked with the delta H, it is already here. It is already in the A levels. But when the Gibbs free energy is linked with the electrochemistry, that is the new topic included to the A levels, which we will discuss later on. Okay, Gibbs free energy change. Free energy means Gibbs, and Gibbs means free energy. It is the energy which is the required by the reactants to go through the reaction. Energy available to the reactants to proceed for the reaction. That is the Gibbs free energy. Gibbs was the scientist's name, so he described this free energy. A reaction is likely to be spontaneous or feasible if there is an increase in entropy and if it is exothermic. However, some endothermic reaction will occur if there is a large enough increase in entropy. The interaction between enthalpy changes and entropy changes determines if a reaction is feasible. It is given by a quantity known as the Gibbs free energy change. The relationship between these quantities under standard condition is this. You are required to find the spontaneity or feasibility of the reaction in terms of the Gibbs free energy, because Gibbs free energy includes the or you can say Gibbs free energy interacts with both the enthalpy and the entropy. So when both the factors are included in the same equation, you you get the value of Gibbs free energy represented by delta G naught. Delta G naught will check if the reaction is spontaneous or feasible. Gibbs free energy is given in kilojoule per mole units under the standard states and standard conditions. Delta H, as you know, in kilojoule, delta S will be converted into the kilojoule because previously it was in the joule, so you will convert the value into the kilojoule, and temperature is in the Kelvin. So this is the equation for this. If delta G is negative, the reaction is spontaneous and is likely to proceed on its own. If delta G is positive, the reaction is not feasible, and at equilibrium delta G is equal to 0. They have summarized all the factors in this table: delta H, delta S and delta G. Putting all the values in this equation, what you get? If you apply delta G equivalent to negative, so here it is the negative, delta H negative means it is the exothermic reaction, and delta, if you apply delta S positive over here, and delta S positive means increase in disorder, then you get the value of delta G negative, and delta G negative according to this statement means spontaneous or feasible. So this is the feasible reaction. So what they have said, if you include delta G is equal to minus delta S minus of the delta H, and this value minus delta H, and this value is this negative is between here, and positive value for the delta S, then you will get a value in negative, and this negative value means that delta G is a spontaneous, this reaction is spontaneous. So this is the one method to this is one case. So, and the other case in which delta H is positive, now that you have now the equation, you can simply put the values and find the value for the delta G. If you get positive value of the delta G, then it will be a reverse case, it will now be not a spontaneous reaction. If delta G gives you a positive value, it will give that reaction is never feasible. Do you get this whole idea? Some more explanation about this. In other situations, the temperature at which a reaction occurs will ultimately determine whether or not it is feasible or spontaneous. The point at which reactions just become spontaneous or feasible is when delta G is equal to 0. So you have to memorize this point. The point at which the reaction just becomes spontaneous or feasible is the value when delta G is equal to 0. And when you apply this 0 on this equation, delta G is equal to 0, then you get this delta H minus delta Ts. Shift this term to the left side, you get delta H is equal to T delta S. It is the point of feasibility. Point of feasibility has this equation. And when do you get this delta G is equal to 0? When delta G is equal to a reversible reaction is at equilibrium or a change of state is occurring. We can use this to calculate the change in entropy in a system at the temperature. At the temperature when delta G is 0. You will be required in a questions to find the temperature. To find the temperature at the point of feasibility. This is the point of feasibility when delta G is equal to 0, and at the point of feasibility you can also describe this state in terms of the equilibrium, that at equilibrium delta G is equal to 0. So both means the same. it means delta G is equal to 0.
Yeah, I feel like I'm gonna have to actually do some questions in order to fully understand.
Yes, here's the question. Let's go through the question quickly. Use the values in table 23.6 to determine whether or not the reaction given is feasible at standard temperature. We have this whole equation. Then we have this table. This gives the values of enthalpy and entropy for all these substances, means enthalpy for the reactants and entropy for the reactants, enthalpy for the products and entropy for the products. Answer: use Hess's law and the enthalpies of formation for table to calculate delta H for the reaction. Because we have to apply this equation, delta G is equal to 0 is equal to delta H minus T delta S. We have to apply this equation. So for this equation we need all the values. First of all, we need the delta H. How can we find delta H for this type of the reaction? If you recall your AS formula, what is the formula to find the delta H here?
Bond breaking minus bond forming.
There's another way to say the same.
Product minus reactant.
Yes, products minus reactants. Simply put the values of products minus reactants, but you definitely have to consider the moles as well. Here they have found the value for delta H here. Delta H is the they have interchanged the terms, but it is the same. Here they have written the products and they have written the reactants here. It means the same, products minus reactants, because it is minus over here. So they applied the values and they found the value for the delta H over here. After that they found the value for delta S. Delta S has the same formula, products minus reactants. We are given the values of entropy in the table. So using this equation, we know that entropy for the Fe2O3 means it is multiplied by 2. So and Fe2O3 is 87.4, so it should be multiplied by 87.4 multiplied by 2, and same goes for the all other species. So they calculated the value for delta S. Now they have the values for delta H and delta S over here. One more thing, since the delta S was initially obtained in joule per Kelvin, it was now converted into kilojoule by dividing it with 1000, because you are moving to a larger value from joule to kilojoule. After that the temperature is understood. At standard condition it is the 298 Kelvin. Now applying the formula, delta G is delta H minus T delta S. Putting all the values here, you get delta G equivalent to 300. Now you see the sign is positive here. So positive sign means the reaction is not feasible at standard temperature. So this is what they have described in this type of the numerical. And it is now almost complete. The chapter is almost complete. I will provide you these photos. If you want to study these smaller topics, do give it a study and let me know if there is anything which is not clear to you. Okay?
No, I understand so far.
Okay. Then this chapter is also in your loaded run book, so I think you should also give it a read and let me know about this as well. Okay?
Okay.
So I will provide you the worksheet for entropy and Gibbs energy. So try to solve some question, but also try to complete your previous questions as well.
Okay.
Alright, so we'll meet tomorrow in our next class.